Good evening, everyone. Am I audible? Okay. Are you able to hear me clearly, loud and clear? Hello, hello, hello. Sure. Okay. I hope everything is fine. Good evening, and welcome to the week 6 problem solving session. Yeah, yeah, sure. I'll take your questions. So, you're in the week 6 of this course on programming data structures and algorithms using Python. So, as you all know, it is brought to you by Professor Madhavan Mukund from Chennai Mathematical Institute, and I'm your TS Syed Shabir Ahmad, and I'm from Department of Applied Mechanics and Biomedical Engineering in IIT Madras. So, I'll be taking these tutorial sessions. Till now, we have completed 5 weeks. For 5 weeks, we have completed 5 sessions, and like this is the sixth week. I think you have a deadline to tomorrow, I guess, to submit the assignment. Maybe there is a short quiz this time. There is no programming assignment, I guess. So, nevertheless, we'll try to revise the things which have been taught in this week. Hope you all have uh, watched the lectures completely of week 6, and hopefully we had understood them. Even if you haven't understood them completely, we'll try to see things how um, we can improve our understanding through this session. Okay, so I hope you have gone through all the uh, sheets which I have uploaded in the Google Drive. I hope you all have that link. Hopefully uh, you guys are able to solve all of those. Okay. So, okay. 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 So in this week, the week 6, we have seen stuff about backtracking and uh, Jenkins problem and various data structures like our sets and stacks, queues, heaps, max heap, priority queues. We have seen different things related to these, whatever I have told you. So we started with, I think, N queens, and we also saw about the global declaration of variable and when it is required and when it is not. So we'll see those things, revise it again. Okay. So we go to the course and see in the week 6. I think there is only one quiz this week. There is no programming assignment, and the questions are also very easy. Hopefully, you can just do that. So in lecture 1, we have seen about backtracking and NPTEL problem, and then we saw how we can code it in Python, and And then we saw how we can get all the solutions uh, of all the possible solutions for the n-queens problem. Both the codes are given here. Like you can click here and get the codes. So if you click here, you will get the code like you can see here. So the code is given to you. Like you don't need to write it, but of course, like you have to learn how to uh, write the codes without looking at it. So hopefully you can do that as well. But for reference, both the codes are uploaded in the course page itself. And then we saw about global scope nested functions, like how you can define a function within a function. And we saw about generating permutations, like how you can generate permutations. Uh, we'll see that, we'll revise it again. And then we saw sets, stacks, and queues. And then we also saw about priority queues and heaps. Uh, okay, so these are all the things which we went through this. So if you go through this, so let's start with a few questions. Like hopefully, if someone answers, uh, I hope you have seen those. Um, we have you have seen the videos, I guess, the lecture videos. So, so if you see this first question, uh, why do you think we should undo a move uh, in backtracking? Like, why do is it required or is it uh, if it is required, why is it required? Can you remember anything about this? Anybody? Okay. 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 Yeah. Screen is not visible. Weird. Sorry. Uh, I was thinking that I was sharing the screen all this while. Now you can see the screen, right? Yeah. Yeah. Somebody has answered. What did you answer? Uh, we need to go one step backward to check another combination for us. Yes, Sonal, you're right. So in backtracking, like we saw in this uh, we saw in the n queens problem, right? So we need to like we check first. We start. Let's say uh, let's just let's just go to share the screen here. I'll write explain. That would be better. Yeah. I hope you can see the screen, right? Mm.
Yes.
Yeah. Okay. So in backtracking, so let's say I have this uh, 3 cross 3, 3 by 3 grid or kind of a board which resembles a chessboard, but it is not a chessboard. So let's say if I place a queen here, initially I'll start with the row 0, then row 1, and then row 2. So because index in Python starts with 0, so that's why I'm writing it as row 0. And this is column 0, this is column 1, and this is column. So whenever like I have to place queens in such a way that one like no queen attacks the other queens. So like if I keep a queen here, like initially I can start with here, or I can also start with here, or I can also start with here. So you have three choices in the beginning. So what will we do? Like we will start with 0, let's say. So that is our choice. Like we can start with any of the column in the first row, but for time being, we'll start with here. So then you can see that row in first row and in first column, you cannot keep anything because this and this is being guarded here. Let's say if you uh, see this diagonal also here, this and this both are also have been attacked by this queen. Let's say I will use different color. So this, and this. So this queen at 0 comma 0 is attacking all these diagonals. So you cannot place any other queen on this locations. So in the red crosses. So now if I have to place a queen, so in the second row, or sorry, in the row 1, then I have only one choice. That is, I have to keep it here. So where is that? I have to keep it here. So then I have to go to the next row. Now you can see this row is also being attacked. This row, sorry, in this row, this uh, location is attacked by this queen, and the other two locations are also being attacked by the first queen, and this queen as well. So there is no possibility of placing the queen. So what we have to do? So we have to undo the operation. So now I have to remove this queen. Okay, I have to remove this queen from this position and place it somewhere else. But there is no possibility of placing it here or here. So what I have to do again? I have to backtrack and go to this first row. Now I have to go to first row now. So I have to remove this. Now if I remove this, like now if I remove this, the first queen from the 0 comma 0 box, now all the squares are free. So what I'll do, I'll keep it here. I'll keep it here. I'm trying the other square. So now let's say this, and this box and this box and this and this are under attack. So now you can see I cannot place my queen anywhere in the second box also. So this is also not possible. So what we have to do again? We have to try another combination. Again, backtrack. So now I'll take this square. Now if I take this square, this, and this are being attacked by this queen on 0 comma 2, and now only this is possible. So if I place it here, now you can see I cannot place any queen. So in this, there is no combination possible at all. Like I cannot place three queens in a 3 by 3 grid such that they don't attack each other. So like I have tried all combinations by going by doing the backtracking. So that is how we do the backtracking. Like if something is not possible, like we go and check, uh, we go back to the previous step, undo it, and try some other combination, and repeat the process. So this process will go on till you find a possible solution. If you find a solution that is good enough, in this case, like in 3 by 3, we are not able to find a solution. So we'll just leave it and say that there is no combination possible for this. So like that, we can go about backtracking. So let's say if I take instead of this, if I take a 4 by 4 grid, right? Instead of this, let's say if I take a 4 by 4 grid. Okay. Let's say first I'll keep the queen here. Okay. This is my position. And I'll start with this. Like you can start with this, or this. That is our choice. Like we can start with anything. And you can see here, this queen is attacking this, and this diagonal boxes as well. So first row, first column is like entirely attacked by the queen, and this diagonal is attacked by this queen. So now, if I have to place the queen, like I can place it here or here. So I have two options. I can place it here or here. So let's say I'll place it here. Okay. Now you can see this is attacking this square. Uh, this will attack here, here, and here. So now you see that this is not like if you row 2 is also occupied by the row 1 is also occupied by the queen. Now we have to go to the next row. In the next row, you can see that all the squares are attacked by the previously placed queens. So this queen and this queen are attacking all the squares possible in the row 2. So what I have to do again, I have to backtrack. So if I have to backtrack, what I have to do, I have to remove this. I have to remove this queen and whatever the squares which it was attacking. So now I have removed this, and I have to try another combination in which this row 1 queen can be placed. So I can now place the row 1 queen in another location, which is 1 comma 3. Now you can see that I can place it here. So now you can see that this is attacking. Just give me a minute. It's okay. Yeah. So now, I hope the screen is still visible. Yeah. I have to record also. Sorry. Yeah. So now you can see that this queen will attack here, here, and here. Like that, we can see whatever the possible stuff, whatever the possible combination. So this is not attacked. Sorry, this I have wrongly marked. But now, yeah, and yeah, these are all the squares which are possible. So now you can see again. I have to place a queen here. Only possible location which is left is this. So now this is also not possible. So here I cannot place a queen because this is attacked here already. So like this, we try out. We go deep into one combination. So we'll start with 0, 0 comma 0, and we'll try all the possible combination with 0. Uh, uh, then you go because this is not giving any favorable solution. Again, I have to undo all of this, undo all of this. I'll remove everything, and now I'll try with this here. So now I'll try with this square. So now you can see this is attacked, this is attacked, and here, 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 it is attacked. Okay. Now I can place. I can place my queen only here, right? So only this is the possibility which is left. Sorry, right? Only I can place it here. In the first row, only one place is not attacked, which is 1 comma 3. Now I can place my queen, and now the latest attack squares are this, right? Now I can place my queen here. Only one possible location is left, and now this is also attacked, and this is attacked, and you can see that this is left and this is not attacked. So the finally I can place a queen here. So like this, we try different combinations. We go deep into one combination, and we undo everything. We try each combination and we undo everything and go about it. So like that, we do backtracking. So now you can see that this is similar to what we also studied in. We learned in stacks, right? So in stacks, the philosophy is last in, first out. So whatever the previous queen which we are putting, like if we want to undo it, so we will go to the previous row and we will remove that queen. So you can use stacks here in backtracking or in the in queens problem. So that is a kind of data structure which is required here. So you have to remove the previous column, previous the last added column in which the queen has been placed, that we have to remove step by step. Like we go back. So from the back we'll keep on removing. So in backtracking that is done to undo the uh, operations. So like that, so you can see that I got one solution here successfully, which is my here you can see this queen attacks here and here, and this queen attacks here and here, right? And this queen is attacking here. Oh, yeah, this queen attacks here, and here, right? So you can see no queen is there in this attack path of the first queen. In the second queen, if you check here, and here, no queen is placed in this attack path. And in the third queen also, if you see, it is attacking here. So finally, this is the non-attacking square left, and we'll place the queen here, and we successfully have a solution here. So similarly, we can also try with uh, instead of taking this, we can also go with the other possible combinations as well. Like if you want all the solutions, like you can like this is the first solution which we got. So if you want all the solutions, like zero is entirely explored, right? So zero, sorry, this 1, 1 is entirely explored. Sorry, 0, 0 square, placing the queen at 0, 0 square is entirely explored, and 1, 1 we have tried. So now you can go about all the other combinations as well. So you can also we can also write something like this. Uh, so we'll start with the empty. We can, like, let's say if you want to write a recursion tree for it. So we'll start with the empty list. So in this list, we'll just take a one-dimensional list. In this list, the index will denote the rows, and the the numbers which goes in the list denote the columns of the grid. Okay. So first we started with 0, 0, right? So, or let's say first we will start, like, these are all the four possible combinations, right? So first we will start with 0 column, and we can also start with first column. We can also start with the second column, and we can also start with uh, third column. So in the level one, while placing the queen in the zeroth row, we can put it in the first column, zeroth column, first column, second column, and third column. Then you go, you can then we go and we see, if we see here, if I put the queen here, then this, as I said, this, and these are the attack. So now in the second row, if I have to place the queen, there are two possible combinations. One is in the second column, I can keep. In the first row, if I want to place the queen, I can keep it in the second column, or I can keep it in the third column. So in this list, so I can keep it in the first column, in the second column, or I can keep it in the third column, right? So like that, if I go let's say if I keep it here in the second column. So like you can see here, this index of the list is there, right? Index of the list. This is 0, 1. So this denotes the row. Okay, this denotes the row, and the number assigned to this index is the column number. Okay, so that you have to remember. So we are, like, instead of taking the locations like this, we are directly taking, like, we are directly taking a single dimension array. So to make our computations more efficient. Okay, so this also, in the zeroth row, the queen is at zeroth column. In the first row, the queen is at third column. Okay, in the in this combination, in the zeroth row, the queen is at the zeroth column, and in the first row, the queen is at the second column. So for this also, let's say if I have placed the queen here, this is attacking here, here, here. So no, nothing is possible now because all the squares are attacked. So I cannot take this combination. So below this, nothing will go. So this combination, like I have gone from here to here, so you backtrack now. So we basically remove this queen, right? So we basically remove this queen. We go here. This is backtracking. So we go here, and instead of that, there is one more possible combination, right? So we go from here to here. So 0, comma 3. So we'll try out this now, right? So now you can see if I place my queen here, so this is attacked and this is attacked, right? And this is attacked. So now again, after placing successfully, I have placed the queen, and then next I can, if I will go to the next level. In the next level, in the second column, okay, in the second column, sorry, in the second row, I can place the queen only here, which is the location is second row and in the first column. So in the first column, I am placing the queen in the second row. So as I have said, this is my zeroth row. In the zeroth row, queen is at 0, comma 0. In the first row, the queen is at 1, comma 3. So this is 1 and this is 3. And in the second row, you can see second row, the queen is at first column. The queen is at first column. Okay. Now you can see again this is attacking this square. Now I cannot go below this. I cannot go below this. So what I have to do, I have to again backtrack because there is no square which is not attacked. So what I have to do, I have to remove this. So I'll go backtrack. Now if you remove it, if you uh, remove this, can you place this queen anywhere else in this column? No, because all the squares are attacked by the other queens. So again, I have to remove this also. So I have to go from here to here. So I have to remove this as well. So again, so now instead of 0, comma 0, I have to try 1, comma 1. So like that, again we'll start with this combination, whatever all the possible squares are there. So like that, we go and explore our recursion. So this is how recursion happens, and this is how backtracking happens. So you try, like, you go deeply into one combination, check the solution, check if the solution is there. If it is not there, you go backtrack, you undo all the moves and try other combination. So like that, we have to do. Okay, understood? I hope you have understood this concept. Hopefully this tree had made some sense in your minds, and you have got some idea. Okay. So in backtracking, what we do basically build solutions step by step. If we get stuck somewhere, we undo the last step and we try the next option. Okay. Like that, let's I take I'll share screen again. let's say if I have my Jupyter notebook. So this is how, let's say, this is how you can write a function for your backtracking. Now you can see here, this is the function. So in the row, like for each valid column, you place the queen. If if it is the last row, right? Like if it is the last row, let's say if we reach the fourth row, then there is no other like you place the queen and nothing else is there. So you got some solution, you record the solution and you get out. Else, like uh, if it is not the last row, what you do, you again go to the next row, right? Like we go from zero to the next row, which is row one. And if we have already placed the queen in the row one, then again we go do row plus one, which is we go to the row two. So like that, we go and do this. Like you can see that this is a recursive function here. So So backtrack is calling itself here. So this is not a like this is not a solution. Like you can say this is a pseudo code. So if it is possible, you backtrack. Like if no solution is coming out, like what you undo the placement and you go back and do the whole process again. So you go to the other column, each valid column, and you check if the solution is possible, and we continue doing like that. So so the answer is like, why do we need queen undo, why do we need to undo a queen placement, or why do we undo a move, is because we, without undoing, future recursive calls will inherit the incorrect board state, right? So like if you have, like if you don't remove the previous queen, like you cannot place like the queen such that it is not attacked, right? Like you have to undo the board position. So board position should be such that no queen is attacking any other queen. So that's how, like we have to explore all the possible combinations. Like if it is not possible, go and that do everything. So like that we can do. So let's say if I have uh, this function instead of this. Now you can see, we'll see what is the nested function also in this. let's say this is the function which will help me explore uh, all the possible solutions. Now you can see that like how to check like if a square is attacked or not. So that logic also we have to remember. So we have to check like after placing the queen. Let's say if you have placed the queen in some row and some column, the first queen, we have to check if the queen, if the square which we are putting the next queen is in the same row and in the same column of the as of the previous queen has been placed. Because like if it is falling in the same row and falling the same column of the previous queen, it means that we cannot place the queen in that row and in that column because the previous queen will attack all those squares. And one more thing we have to look at is that we have to look the diagonals also. So because the queen is attacking diagonally also, so we have to look what are all the boxes or what are all the positions in our next row in which we are trying to keep the queen are attacked by the previous queen. So to do that, we have the logic, right? Like we have to uh, check board board of I means like we have to see in the row which we are keeping the queen, in the row which we are sorry, in the column which we are keeping the queen, and in the previous column, call means like the column of the previous queen which you have already put. Board of I means the column in which you are trying to check if the column is possible or not. So if this difference, if this difference is equal to I minus row, I is the row in which I am checking now, and row is already the rows in which previously the queens have been put. So we have to check this difference, and if it is coming out false, then it is okay. We can proceed to keep the queens in that square. Otherwise, if it is coming true, then it means that squares are being attacked by our the previous queens. So like that, we have to check whether the square in which we are trying to keep the queen is safe or not. So for that, we are defining this function. So it will take the row and column of the square which you are trying to place the queen. So whatever the row and column of the square in which you are testing, so it will take that row and column and it will do this check if it is like whether the row whether the square is attacked or not. So we have to, whenever we go from one level to the next level, we have to check all the squares using these conditions such that no square in which we are placing the queen is attacked. If it is attacked, then we can't put there. We have to we have to look for some other possible location. If it is also not possible, then we go backtrack and remove the queen, previous queen. Okay, so that's how we have defined this function, and then we have defined this backtrack row. Now you can see that if row is equals to n, like if you have end, like reached the last end, like this is the stopping or the base case of your recursive call. This is the base case. Like if you reach the last row, then finally like you place the queen and you have to print the board. And let's say if it is not the case, then we have to check we have to go to the next row, and again we have to check all the columns in the all the possible squares in that row if they are safe or not by using our safe function. If it is safe, again we have to if it is safe, again we have to like do this, put the queen there. if it is safe, in that row and in that column you will keep the queen. Okay. If it is not, and then you go and backtrack again, we have to go to the next row, right? Like we have to go to the next row. So this is a recursive call, you can see. So this will go on happening like till we hit the best case. So like that, this process keeps on continuing, and this function will help us to, yeah, this function will help us to do that. Okay, let's see. Let's say if I have defined this function, and if I have run now, I let's say if I have to place four queens, right? So if I place four queens, I run. Now you can see this is the first possible solution which is possible. Is in the zeroth row, I can place the queen. I have to place the queen in first column. This we have already seen, like we have drawn in the notebook, and we already saw this, right? This solution, and I can place it uh, in the first row. I can place the queen in third column, and in the uh, second row, I can place the queen in the zeroth column, and in the last row, I can place the queen in second column. So like that, uh, I can write a code which will help me do that possible thing, right? Let's say if you want to start, like even if you want, like let's say all the possible solution, you can write the function for that as well. The code is given in the notebook, like you can go and check. So like that, we can do the backtracking, like you can write the recursive calls, nested functions, and use your programming knowledge and test it out, right? Do a lot of practice, and like firstly, like whenever you try, right, like you try to draw the box, you try to draw the box, and you try to do all the combinations, draw a recursion tree, and first try that, and build your intuition. So by doing on your own, like for small case, like for 4 by 4, you can do that obviously. So like you can check which squares are attacked, and then you can build. So like that, try that, and try to build the intuition first, then you build the logic. So logic is like which square is attacked. So from first row, when you go to the second row, if you have to check, you have to check all the columns in that row are not attacked. So you have to check like if the previous queens are in those columns. That is one case. And again, you have to check the diagonals, right? So for diagonals, you have to check this absolute difference. So all the columns will have same addition. Like let's say if you take all the columns, 0 comma 0, 1 comma 1, 2 comma 2, if you subtract their indices I comma j, then for 0 comma 0 difference is 0, for 1 comma 1 also difference is 0, 2 comma 2 is also 0. So like that, all these fall in one diagonal. Let's say if you have 1 comma 1, and for the, or let's say if you have 0 comma 1, for that diagonal is 1 comma 0. So then you can also check 0 comma 1 and 1 comma 0, how the condition will satisfy. Is that like 0 plus 1 and 1 plus 1 is 1. Like that, you can do this basic calculations, like you can build the logic like that. So based on the logic, you write the code. Okay, try to build the intuition like that, and hopefully you'll be able to do that by doing a lot of practice. Like you will not get anything for free, so there is no free lunch. Okay, so you have to, like, this is a thing which is said, like whenever somebody uh, tries to tell you that something is not easy to get, they'll tell that there is no free lunch, especially in like uh, engineering or like in research. People say there are no free lunches, so you have to do these things, then only you will be able to learn. So then we go to see how we can see the scope of variables in Python. So okay, and in Python, whatever the variables which you define, what happens is that the name lookup happens inside to outside. Okay, so assignment inside the function makes variable local. Okay, so here you can see that I have the assignment inside the function x is equals to 20. So because I have given this as x is equals to 20, now if I print this function, if I, let's say if I run this function, what will be the answer? Can anybody tell? What will I get?
10.
10. Okay, Chris, George.
Sir, can I
Okay.
ask you something?
Yeah, yeah.
Sir, it's not about the question that you're doing now. I just want
Hmm.
to ask you about the course.
Yeah, yeah. Please
Well,
ask.
sir, some of the assignments that I did have not been submitted properly. So when I checked it now, it hasn't been submitted. So if
Okay.
I like start doing my assignments now, and if I actually there's like week 5, week 6, week 7, and week 8 left. So
Yeah.
if I like complete all the 4 assignments, just the 4 assignments right now,
Hmm.
will I be able to get the certification? If I complete the assignments right now, those 4, the only 4.
Yeah, yeah. You submit
Uh,
those like, but 6 assignments will be considered. For remaining two, I think you will be like marked zero. But 4 assignments you complete, like they will take the 4 assignments. Uh, Average
okay.
of 6 they will take. So and again, like you have to give the exam, right? So if you give the exam, like I hope you have applied for the exam. So
Yeah,
if you
yeah,
do
I
that, you
have.
will get the certificate. Yeah,
Oh, okay, so thank you so much.
yeah.
So will there be a compiler in the exam
Uh, no, no.
to check the
I didn't
programs,
understand. Can you ask
So
again?
check the
how will
program
the
if it is
exam be?
working or not?
There will be coding questions also, like how they like programming assignments have been asked uh, in the assignments, right? Like you will be asked programming questions also, like you have to code there. There will be a uh, like how you got a window to compile and run, so that will be there, like you have to do that.
So it won't be like written based, right?
No, 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 it is not a written exam. Okay, it is computer based exam. Like you have to
Oh,
either you will have either programming questions or you have quiz questions, like
okay, so thank you.
yeah.
So we can run the programs and check if the answer is correct or not.
Yeah, so there will be few public cases, those you can test out. Okay, but the main thing is like you have to your program has to satisfy all the private test cases which will be evaluated. You will not be awarded for public test cases. Okay, so your code must be robust such that it should possible like it should satisfy all the test cases.
Thank you, sir.
Okay, okay, somebody answered. Okay, below is the questions that appear in the exam will be similar to. I hopefully Dilavis. I also don't know because I am not involved in that. So the professor who is handling the course will set the paper, and whatever the questions you will get will be from these only. Like, but there will be like the questions might not be direct. It might have some context, like context, right? Like there will be a some kind of a story to it, like you can check my practice sets which I have uploaded in the Google Drive. Okay, so there are a lot of questions which have uh, like which are very indirect, like in taking real time context. Based on that, you have to identify what I have to apply here. let's say you are mm, making a job scheduler, right? Like then you have to use heaps. So or priority queues you have to use. So for that, you have to have the idea. Like, okay, for this question, I have to use this data structure, or I have to use this algorithm. So like that, questions might be there. Like they might not be direct, but those questions will all be based on the concepts which are which you have learned here. Like, so be thorough with all the concepts which I have been taught in the course. Don't uh, don't try to overdo. Like, don't try to learn other things apart from this. Be thorough in this. Like, there are a lot of other stuff also. Like a lot of other algorithms also, other the data structures also. But for now, please stick to this only. Okay, that's what I'll say. And try doing a lot of practice, solving a lot of practice questions. Yeah. So what is the, if I run this, what is the possible output which I'll get? It will print 10. Okay. Okay. Any other any other answer? Nobody has any other answer. Okay. Yeah. Outbound local error. So that's what we will get here. Okay. Then now you can see this is an outbound local error. So cannot access local variable where it is not associated with a value. So now you can see here, because I have assigned the x value in the function again, like after I have assigned here outside. So I have assigned here inside the function as well. So in Python, as I have said, name lookup happens inside to outside. So first, in the function itself, Python will check if something has been assigned to x or not. Okay, because like after print x, like even though after print x, I have assigned x is equals to 20. Because of that, this is a local variable in the function, and this will try to take this value only. So it will not consider this value. So in the function, x is something which is defined like this. Okay, so this will not be a valid thing right now. Okay, so for whatever the x is there in the function, this is the variable, not this. Okay, so let's say if I have removed this, like if I hadn't put this, I just commented it out. Now if I run this, now you can see that the value is 10, because there is no assignment to the value of x inside the function. So there is no local assignment. So what happens is, like, if it is not assigned inside, it will go to the outside. So inside to outside. So name lookup happens inside to outside. So because this is assigned here, x is equals to 10. So now if I print, now if I run this function, I'll get the value is equals to 10. So like that, we have to be careful with this defining the uh, scope of the variables. Yeah. Then let's say if I have given like uh, instead of here, if I had kept it here, then I have probably got x is equals to 20. See, in front of print, if I have put, because already x is assigned equal to 20, now x will print uh, as 20. So if I run this function, it will give me the value of 20. So like that, we have to be very careful, because integers are not mutable. So in like we have seen this in the lecture If this was a list, then it would have been a different case. But because this is an integer, like the assignment is an integer and it is not mutable, so that's why it was giving us the outbound local error. So if I want to do that, like if I want to uh, do it something like that, so what I have to do is like I have to define a global x and x equals to 20. Now, if I had let's say now if I just like I have removed the print, now if I run it, the function has been executed. Now let's say if I run, if I want to print and check the value of the function, the value of x, what will be the output here? What will be the value of x here? Anybody uh, willing to answer what will be the value of x here? Yeah, yeah, it will be 20 because you have defined this variable not as a local variable and you are saying that x is a global variable. So even though you have assigned x is equals to 10 outside the function, because now you are making it global variable inside the function, and you are now reassigning it x is equals to 20. Because of that, if you run this and print the value of x, the value of x is 20. So like that, this scope problem happens. So, like as far as possible, we should try to avoid this, like doing this stuff. Like instead of that, like you have to like prefer pass the parameter, like define x is equal to something, and then yeah, let's see what will happen if we print x. You tell me what will happen. What will be the output in this case? Then let's see. 10 is the answer. Okay. Because you have already assigned x is equal to 10 and you are making x as global variable now. And then you are printing x. So it will obviously take the previous value. And after print statement, we are making the value of x is equal to 20. So now after that, it will change to x is equal to 20. But before that, we are printing. So the value of x will remain 10 itself. So as far as possible, like don't fall in this way of defining the variable in like global and local and all this stuff. Like if you have defined the variable, assigned it outside, like try to pass it inside. Instead of doing this, try to pass the variable through the function as input and try to do like this. Okay. But some cases you might need it, but yeah. So like that, this scope is taken care of in Python. Okay, in the functions. So the next thing in this week which we have learned about is permutation. So permutations means like all the possible uh, ways in which let's say we have the NPTEL problem, right? So all the possible ways you can select uh, all the possible ways in you can place the queens let's say even if they are attacked or not attacked. Uh, then all the possible players, like if you list, then you can say that those are all the possible uh, uh, things which you have. Let's take go to the notebook now. Okay. Let's say you have uh, numbers, right? Instead of we saw how we can generate next possible permutation for letters when you have a list of letters uh, previously, but here we'll see we'll deal with numbers. So now you can see, let's say if you have 1 2 3, so how can we generate the next possible permutation for this? So what we what like let's say this is the smallest possible permutation. Okay, in the increasing order, this is the smallest possible permutation. Okay, and this is the largest possible permutation, 3 to 1, which is in the decreasing order. If you have three numbers, how many permutations are possible? Like if you have three numbers, or let's say three uh, items, like how many permutations are possible? Like hope you have studied permutations and combinations in your 11th or 12th. Based on that, somebody wants to tell like how many possible permutations are possible here for let's say three items which you have. Like it doesn't need to a number right here, but like it can be letters or some other like ball or some kind of items as well. How many possible permutations are possible for three items? Anybody has any answer? Want to take a guess? Six. Okay. How is it six, Shivan? Your answer is right, but how do you generate? Let's say you have n. Yeah, 3 factorial, right? So we know this formula like to get the number of possible permissions NPN, right? So in how many ways we can place n elements uh, in n places? So that's what is a permutation, right? Like that's what we do in permutation. So that is n factorial divided by uh, n minus n factorial, or you can say n factorial by 0 factorial. So basically 0 factorial is 1. So finally I have n factorial. Let's say if you had 10 items and if you had to place in three places in different ways, then that would have been NPR, right? So, or 10P3. So then that would have been 10 factorial by 10 minus 3 factorial. So like that, we know permutations. We generate the number of possible permutations. So I hope you all remember this. So here we have 3 factorial number of possible permutations, which is 3 into 2 into 1. We have 6 possible permutations, which are possible here. So the first and the smallest and the greatest possible permutation, or the largest possible permutation, we have listed out. The remaining uh, 4 permutations we have to, let's say, generate. Okay. So here you can see, like, we are basically, we want to generate permutations, the next permutations in the dictionary way, or dictionary order. So whenever I say dictionary order, like if you are someone who has, like if you are a millennial or a Gen Z, who was in school from maybe before 2010 or till 2012 maybe, like you might have used dictionaries. So in dictionary, how like letters, or like how words are placed, right? Like in alphabetical order. So all the letters start with A will start first, and then the letter starting with B, and then the word start with A, word starting with B, and word starting with C. Like that, it is arranged. In A also, in the second letter, uh, if in the second letter you see, all the letters starting with A will be placed first. Then all the letters starting with A and B will be placed first, and all the letters starting with A and C. So like that, lexicographically, things are placed in the dictionary. So like that, I want to use that, like, so dictionary order, and try to generate the permutations here. Okay. So to do that, so like here also, like in number, like ABCD, you can say as assuming, right? Like here dictionary order is, uh, it will start with 1, then it will start with 2, numbers start with 2, and then when numbers will start with 3. Like that it will happen. Okay. So now if I have to generate uh, the possible combinations, permutations. So what I have to do is I have to go from backside. I have to find the first decreasing index from the right. Okay. So I'll go from here 3, and I'll go and check. Now you can see this is decreasing. So 3 to 2, this is decreasing. So this is my first 0, 1, and 2. So my first index is decreasing compared to the second index, right? So what I have to do, I have to swap these two. I have to swap these two. So if I swap these two, what I'll get, so I'll make this intermediate step now. So 0, 3, and 2. Okay. Sorry, 1, 3, and 2. So this is my uh, smallest possible permutation. Okay. The next permutation which is possible after 1, 2, 3 is 1, 3, 2. Let's say now I have to generate the next possible permutation. Okay. 1, 2, 3. 3 permutations we have, and 3 remaining we have to get. So from here to here in the dictionary order, I have to get the next permutation. So for that, I have to again follow this algorithm. So in the algorithm, so there are 3 steps, right? So in the algorithm, for this, for permutations, next permutation, to find out the next permutation, remember these three steps. Find uh, find first decreasing index from right, index from right. Okay. Then we go swap with next larger element. Yeah, that's what we did here. Swapped with next larger element. Then we have to reverse the suffix. We will see reverse the suffix here. This we haven't done, reverse the suffix, but we will see. So now to find out the next possible, you can see here, find the first decreasing index from right. So I'll go from 2 to 3. So it is increasing. And 3 to 1, you can see it is decreasing. So this is the first index. If I'm going from right, which is where decrease is occurring. So then I have to swap. Then I have to swap with the next lowest, larger element. So compared to 1, 3 is also big and 2 is also big. But the lowest number, which is greater than 1, is 2, right? So I have to take the next larger element, not the largest of all this. Next larger is 2. So I will swap 1 and 2. Okay. I will swap 1 and 2. So now I will get 2, 3, and 1. Now the next part is we have to reverse the suffix. So this is in decreasing order, right? So we have to reverse the suffix is this part. Okay. We have to make this like this. Okay. Obviously, right? Things are starting with 1. Things starting with 1, we have already found out in dictionary. Things starting with 1, 1, 2, 3, and 1, 3, 2 are the possible things. Then after that, when things start with 2, the next possible thing, smallest possible permutation, is obviously should start with 1. So that's why we'll reverse the suffix, right? So this is my next possible permutation. Now again, I have got 3. Now 2 are left. So again, I have to check where the index is decreasing. So you can see here, this is decreasing. So we'll swap it. So this is my next possible permutation, next smallest possible permutation. Okay. Now again, so we have how many? We have got 1, 2, 3, 1, 3, 2, and 2, 1, 3, and 2, 3, 1. We have got 4 already, and we have this last one. We have to find out another possible permutation. So now you can see here. Here it is increasing, and here it is decreasing. So this is the first index from the right, which is increasing. So I have to swap this with smallest, the next larger element. So the next larger element, when you compare 2 with 3 and 2 with 1, so 2 is like obviously 1 is less than 2, so you can't swap it with 1. So but 3 is greater than 2. So 3 is greater than 2. So we will swap it with 3 and 2 and 1. Okay, but you can see that this suffix again we have to reverse the order. So this is in decreasing order. We have to make it in increasing order. So like this, if I check the permutation, this is my last possible permutation. So we have got 6 permutations. See, all these are in dictionary order or lexicographical order. Okay, lexicographically we have arranged, right? So you can see first all the words or like all the numbers which are starting with 1 are placed first, right? And then in 1 also numbers starting with 2 are placed first, right? Then numbers starting with 3 are placed, obviously. So like that, uh, possible combinations of starting with 1 are done. Then we go to 2. In 2 also, first we will start with 1, and then we'll see, obviously 2 again cannot be put because like we are not having any duplicates here. So 3 is the next possible thing, and we have put it here. And again you have to, if we see, we go with number starting with 3, and you can see first number starting with 1 after 3, and number starting with 2 after 3 are placed one after the other. So like that we can generate next permutations, lexicographical order, okay, or dictionary order. You can generate the permutations. So you can also write a code for it uh, to find out the next. Yeah, these things will these steps will work for more than 3 elements also. These are universal steps. This is the algorithm basically. You have to remember it. Okay. Okay. So next, we had seen about I think this as well. Okay, I can store this stuff. Permutation. Yeah, you can do this coding if you want. So next we can see about sets actually. So there are. Uh, so what happens? Let's say there are, if there are duplicates in set in Python, there are, like we have seen till now. I think we have seen only lists and arrays and dictionaries, and what are all the other data structures we have seen? I think only these two, and also tuples and lists. Lists are arrays or dictionaries, and tuples we have seen, I guess. So next we will see, we are in this week we have learned about the other data structures also, which might be helpful. So one of that is sets. In sets, let's say if you have s is equals to uh, s is equals to 1, 2, 2, 3 is there. Now if I print s, what will happen? What will be the output here? If you run this, if you define a set like this, and if you run this in Python to print the set, what will be the output? Yeah, 1, 2, 3. So in the sets, there will be no duplicates. In set, each element will have only one occurrence. Okay, so duplicates will be removed. So it will have only one occurrence. So that will be the output. Okay. So then we went about learning stacks and queues. Okay. So stack is basically uh, like you have some newspapers or books. You keep one over the other, right? Like you keep one over the other, one over the other, like that we keep. So in stacks basically like books are like if you remove it, this will be like if you remove if you try to remove like possibly you can remove, but like this is like playing Jenga, right? So if you remove it, it might fall off completely. So the data structure stack in the data structure stand, we have this 1 minute. I'll just take a call. Okay, sorry for that interruption. Yeah. So in stacks, we have this philosophy, right? Whatever the thing which you keep last, you will take out that first. Okay. So whatever the thing which you keep last, like let's say, even if you arrange it like this, whatever you keep, let's say, stack numbers like this, whatever you keep uh, at the end, like let's say if you have kept five, like you will remove five first. So we have the philosophy of LIFO, or you can say last in, first out. Okay, last in, first out. So this is what is done in stacks. Like whenever you use stacks, this is what is done. Like we have done the backtracking in N-Quin's problem, right? So there we have seen how we undo, right? So like you can see here, here I have drawn this recursion tree, right? So whatever the uh, last row is there, from that we are removing the queue. So this is basically a stack. Like you can use a data structure of a stack here. Like whatever is there, like whatever is added last is removed first. So you can use a stack here. So that's what happen in stack. Okay. So compared to that, like if you have a queue that has a different philosophy. Uh, in queue, we follow what is known as FIFO, or you can say first in, first out. So whatever the thing which you uh, put first is going to be out first. So as the name suggests, like you can imagine a queue, right? Like if somebody is standing in a queue to take tickets, the first person who is standing there will take the ticket first and he will get out first. So, and the last person will obviously get it last. So, like that, we can also use like queues as a data structure whenever it is required for us to do this kind of stuff. So where do we do it? Like we have seen this problem of placing a knight, right? Like if we have a knight and you want to find out the shortest possible path, uh, shortest possible path from one location to the other. So to do that, first what we do is we take all the let's say if I have a queen in a chessboard, let's say I'm just drawing a 4 by 4 uh, board. I have a knight here. Knight. I'm just saying knight. So knight obviously it can move in this kind of way. So it can go here, or it can go here, or it can go here, or it can go here, right? Or let's say can go from here to here. So imagine like it's take a better to take a bigger chessboard, the 8 by 8 chessboard. So if you have a knight, let's say if you have a knight here, and you have to uh, see how this knight can reach, let's say this square. Let's say this square in the shortest possible way. So what we do is we basically take all the possible. First, we'll check all the possible shortest uh, single steps possible from this knight. It can go here. This knight can go here, or it can go here. Can go here. So like this, we'll search all the possible one steps. Okay. So first we will search all the possible if we can reach this square in first step itself. Then if it is not possible, then we generate all the possible uh, two-step solutions. So two-step means like from here to here and then from here to here like that. So we'll check all these kind of all the possible combinations like that. So you generate all the possible combinations level by level. So if you can reach the square in one step, or if you can reach the square in two steps, all the possible combinations you check. So in the second step, you check all the possible combination. If it is possible, then you give that solution. So what you are doing here, so we are uh, we are doing the breadth exploration here. So basically we are uh, taking all the possible combinations for the first step, like, but while placing the queen problem such that no queen is attacking each other in the n queens problem, so we did the opposite thing, right? So we took one combination, like we took one square, we took one combination, we went deep into that. So we went deep into that and explored everything. If it is not possible, we undo our squares, like we undo all the process and we go to the other combination. So that is depth first exploration. this problem of placing a knight, this problem of uh, taking a knight from one square to the other, like you, if you want to check in how many possible steps you can bring the knight from this square to this, minimum possible steps required to bring this knight from this square to this step, this square to this square. So in this problem, we do breadth first exploration. So this is called breadth first exploration. The breadth. Why am I saying breadth? Because we first, like, we don't go here to here and to here and to here, something like this. So we are not taking a single possible combination, and we are not exploring it fully, right? So we are taking all the possible first step combinations, like single step combinations, and we will check if we can reach the square in single step. So we are checking all the possible combination in the first step. So we are exploring all the breadth of it. So that's why this is called breadth first exploration problem. Okay. So in this, we have to use queues, like you can see here. So you will generate, right, like what are all the possible squares. So uh, you will write what are all the possible squares possible in the first step itself, like you will generate, and in that you will start checking if the knight can be placed like uh, if this is the location of the knight, if this is the location, or if this is the location, or if this is the location, you will check one by one. So if this location is reached, whatever x comma y, let's say, if this location matches with your list, what if your location matches in the locations list. So first, so basically whatever the number, whatever the list which you are taking out, so you will remove it. So if this is not possible, you will remove it. If this is not possible, you will remove it. If this is possible, you will keep it. So like that, we will use here first in, first out, or a data structure called queue will be useful here. So stacks you can use whenever you have depth first exploration, like we do in the NPTEL problem. Queues we can use when we have breadth first exploration. Okay. So queues are first in, first out. Stacks are last in, first out. So that is what. Uh, so we have like. Uh, so you can answer this question, like we have. Why does you use breadth first search? Why does breadth first search use a queue and not a stack? Because we are not going deep into one combination. So if we went deep into one combination, we would have like used the stack, because we do backtracking and remove the elements from the last. But here in breadth first search, we are taking all the possible combination in the first level, and we will see one by one. Whatever comes first, we will check. If we are reaching, then it's fine. If it is not reaching, then we will remove it. Like that we do. So that's why queue is not stack is not useful here. In this case, we have to use uh, uh, queue here. So stack is not useful. So queues will ensure. So queue will ensure level by level exploration. Level by level means, in this case, if I can reach the square in one step, that is first level. If I can reach the square in two steps, that is the second level. So in each level, you check all the possible, you explore all the possible combinations. So in each level, you explore all the possible combinations. So that's how queue can be used in breadth first search. Okay. So these are like you should be careful. Like depending upon the problem, you have to check. Like you have to be careful and use the proper data structure. So if this is a depth first search, then you have to use a stack. If it was a breadth first search, like the night problem, then you have to use a queue. Okay. Instead of queen and queue problem, then like you might get some other kind of real world situation here. So like you have to develop the thinking, like where to use a queue and where to use a stack. Okay. So yeah, in for checking the level 2, you have to have the coordinates of first level and second level, both you have to have. For each first level, you should have all the second level combinations. So like that you have to do. So then we have the last thing I think which we have learned in this week is heaps and priority queues. So basically, these are heaps are like complete binary trees. Binary means like each uh, node will have two nodes, and the one on the top is called a parent, and the other two are called children. So, or you can also call this as max heap. So, like this, we will have heaps, like you can have this. So, the last possible uh, node is called as a leaf node, or this is called as a parent, and this is a leaf, right? So, this is a leaf, and these are all children. These two are children, and we have to make sure that if this is a max heap, this number, the parent is always greater than its children. Like the number in the parents is always greater than the children. So you have to make sure that this property is like properly followed. Okay. So the height of, if you want to, let's say, uh, if you want to get what is the height of a uh, uh, this heap, like firstly we can see that we can take powers of 2. In the 0th level, we will have 2 power 0, which is one element. In the second level, we have 2 power 1, which is two elements. In the third level, we can have, or in the second level, this is first level, sorry, and this is in the second level, I can have how many possible elements? I can have four possible elements. So if I want to get the height of this heap, like obviously here we know this is a two level heap, 0, 1, 2. So if I want to get height this as 2, like I can use logarithm of log of base of 2. Like here base is 2 here. That you have to be, that has to be understood implicitly. N is the number of possible or the number of elements here, right? In this, so if you put uh, 2 square, or also like you can like add this, but it's not necessary. Like even if you take this or not, it won't be a, big issue. But this is the like 2 square is the important thing. So if you do like these are like just additions, like you can say you can remove them. So the total number of possible elements, like the level you can get is just by doing this, and this is 2. So log 2 base 2 is 2. So from by like this you can get the height of the heap. So order of log n, or you can say order of 2, right? So like this you can get the height of a heap. And let's say if you want to insert uh, something into a heap. So let's say if I have a heap, I have a heap something like this. Let's say I have 10, 9, 8, and something like 7, 6, and I'll just have let's say 5 here. Now, if I have to, uh, let's say, if I want to enter, if I want to insert here one number, like let's say I want to insert maybe 11, maybe 11. So I will insert the number first at the last possible uh, location. So here I this was in this binary tree to complete it. So first I had to fill this first, right? So this was empty. Like now I have added one element to it, 11. So in the last possible position, I have to insert that element, whatever I want to insert. Then after that, I have to check this with the parent. So now you can see the parent is smaller than the child. So what I have to do, uh, I have to swap this. So I have to swap. Now you can say this. I have to make this 11 and I have to make this 8. Okay. Now again, I have to check the parent of this as well, grandfather. So you have to check again with this as well. Uh, Now if you check, this is parent is lesser than the child. So again, you have to swap these four. So instead of 10, here 11 will come and here 10 will come. Now you can see how many levels, like how many steps I am taking here is of order of log n, right? So which is nothing but height of the heap. So I am going from here to here. So it will take this much computational complexity to do the insert operation. So 0 to 1, 1 to 2. So like that, if you know the number of possible elements, like we already saw, right? So this is nothing but height of the heap, right? So to insert a number in a heap, this is the time complexity or the computational complexity. Let's say if you want to remove the maximum value from the heap. So what we will do? So we will remove the maximum possible, right? So 11 I will remove from the heap. So this has the highest priority, let's say, because the number is 11. You can use this for priority queues as well. So I will remove it. So after removing it, whatever the last element is there, so in the last element, this is the last element, right? I have to replace this with this. Rightmost element is the last element, okay? I have to remove this. So 11 was removed. Now again, you check with your children, the largest child. Which is the largest child? 10. So I have to replace this with 8. Okay. So now this is fine. So the sweep, like the modified, like 11 is removed, the largest value is removed. Again, you can see I had to go possibly two levels. Like the computational complexity for this is also basically O log n. So to delete the maximum value from the heap is also has a computational complexity or the time complexity of log n. Okay. Let's say you have some elements list of elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you want to make a heap of this, so there are two ways. Okay, there are two ways. Like this, we started right. Like we will take one element. We will take one element and insert it, and we will take the next element. We will insert it, and we will take the next element. Something like instead of like 1, 2, 3, like I can take 7 also, right? So do it. So like we did the insert operation before. So we will take each element and we do this operation. So it will take n log n computations or computational complexity is n log n. For each insert, it is log n, right? So for n inserts, it will take n log n computations or steps to do to build the heap and to insert all the elements of this list into the heap. Okay. Instead of that, insert if that place is also filled, then you go to this here. Okay. From the left, you have to go. So you have to fill here. If this place was also filled, you have to go here. Okay. So repeatedly inserting one element after one element, it will take, let's say, if you have 1,000 elements in the list, it will take n log n, right? So n log n of log of 1,000, something like this. It will take possibly 1,000 into 10. This is 1,000 into 10. It will take 10,000 steps to fill the entire heap with the list. Okay. But instead of that, instead of doing this, we use heapify. So in heapify, what we'll do is, like, instead of inserting like this, like if you have all the elements of the list at once, so you will prepare the all the possible 1, 2, 3, 4, 5, 6, 7. Like that. So you will prepare it and you start keeping the elements here first. You will start keeping the elements here. Like, let's say you will keep some elements and then you will keep some other elements here. You will fill this 2 with some other elements. And then you check this and this. And if the parent is bigger than the children, then it is fine. Then if it is not, then you swap. Then again you fill this other possible stuff. So only in the last nodes, like in the last level, we don't have any operation, right? Like we just have to fill it. When we go one level above, you can see the number of elements are decreasing, but we have to check with their children. So for each node, for each element, like you have to do 2 comparisons and like that. So like that, if we use heapify, what happens is this computational complexity, instead of uh, n into log n, it will decrease to order of log n. So it will just take 10,000 steps to build the heap. If you do like that, if you do like this, so you take the last level, fill the elements first, then you go to the next top level, compare with the children, do that stuff. So basically total work if you want to calculate, like it will come out something like this: n by 4 into 1 plus, in the next step, it is n by 8 into 2, something like this. It will done. It will be done like this. So the total number of computations it will take for you uh, is order of n. So you don't need to remember it, but like how to get order of n. But you remember that heapify will heapify will make the number of computations less. Okay, so you should use heapify when you have all the elements to build a heap. You should heapify. You should use heapify instead of using repeated insert to build the heap. Okay. So when all elements are available beforehand, we should use heapify over repeated insert. Uh, okay, like when you just want to do insert, then you just follow the process which we discussed before. Otherwise, you have to use, if you want to build a heap, you have to use heapify. Okay. So these are some things. So we use like whatever the concepts which we discussed, right? So we have so we use backtracking when we have depth first exploration. Okay, when we use when we have breadth first exploration whenever uh, we want to do like level exploration. Whenever you want to do, you have to use breadth first exploration. So in NPTEL's problem, we use backtracking, and in breadth first exploration, we like in the night problem we went about that. So heap is more efficient than the sorted list for priority queue, because we are arranging in levels, right? So in the sorted list, obviously, like you will take it will take n computations, n computations to do some operation, to let's say to insert some element or to delete something. Okay, but in the heaps or priority queues, the operations reduce to log n times. So, like let's say if you have 10,000 1,000 elements, you will take only 10 steps to insert something. Okay, like that, it is enable like it will enable you to do priority scheduling. Okay, so and like in order to build a heap, obviously you have to use heapify because it is linear. Otherwise, the computations, like if you just use inserting repeatedly insert the number, then you will end up doing n log n computations, right? So if you have to connect all the things which we had learned, so stack is a data structure which is used for depth first exploration, and we can use it for backtracking problems. Then we went to queue. Queue we can use for breadth first exploration, right? Like this, you can connect these two things. You can remember this stuff, right? So I think that's all. We have all this uh, um, things. So sorted list compared to sorted list, priority queues are better. Sorry, heaps are better for priority queues compared to the sorted list. Okay. So we have seen all the possible things which we have discussed. Concepts, I think, should concepts should be clear. That's why I try to explain what are all the things, like how you can search the spaces and all. You try to again go back and revise stuff. Like only when you do it, you will be able to remember these things. Again and again, you have to practice a lot. So hopefully, uh, you will remember everything. I'll also update a practice set along with this, like some problems there, practice sets apart from these questions, whatever which we are discussing. Uh, that also I'll upload. So you go through them, all of them, practice and learn, and uh, it will let you help prepare for the exam. Okay. 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 We can stop here today. Anybody has any questions? No. Okay. Okay, guys. We'll meet in the next week. Uh, till then, practice a lot. There is a short quiz. I think you can do it. Like it's not a very uh, huge thing to solve. It's a very easy quiz. You can solve it for this week. Okay. Okay. I'll stop